To finish up our unit on bonding, we're going to talk about forces between molecules called intermolecular forces or attractions, and we call those IMF, intermolecular forces. So we've been talking about covalent and ionic bonds, and we also added metallic and covalent network bonds, and those are intramolecular bonds. Those are bonds that hold a compound together. There's these bonds inside the molecule, okay? So this is an intramolecular bond, and that right here is a shared pair, so that would be a covalent bond. And ionic, metallic, covalent, those are our types of bonds we've already gone through. And now we're going to add the attractions between molecules, and that's called intramolecular forces. And so water is in a cup, which means it has tons of other water molecules around it, and they become attracted to each other. Okay, why? Because they're polar molecules. There's a partial negative charge on this oxygen, which means all the electrons are being pulled up to the oxygen, which leaves partial positives on these hydrogens. And remember, this is just like a magnet. We have a negative pole and a positive pole, and these water molecules actually turn themselves and align so the negative and the positives are aligned and they attract. So these little squiggly lines here is the attraction between these molecules. So this intermolecular force is actually called hydrogen bonding, which is super confusing for people because they think this is a hydrogen bond. This is not. This is a covalent bond between hydrogen and oxygen. This attraction between two separate molecules is called the hydrogen bonding or hydrogen bond. Okay, and really what we're talking about is molecules are sticky. Some are stickier than others, and this attraction is the stickiness. So how sticky are they? That's about the forces and how strong those intermolecular forces are. So we have three types of forces between covalent bonded molecules and one with ionics, and we're going to talk about those. London dispersion force is our first molecular force. It's also called van der Waals, and LDFs or LD will be our abbreviation. They're generally very weak, and they are in every single substance. And that it's because they're just due to the motion of electrons. Remember that electron cloud is all about probability. And there is a probability that all the electrons will clump up just for a brief moment, not forever, because then they'll start spinning around. But there's a probability that several of them will be here at one time, which would cause a temporary pull on that molecule. So temporarily, this would be negative and that would be positive. And it would attract another molecule that normally doesn't have a pull, but for a moment, it would have a negative and a positive. Why? Because those electrons are whizzing around, and for a brief second, there is a probability they might be clumped up, okay? Now, what's important to know is if we are comparing two different molecules, so let's say I have methane and octane, those are both nonpolar molecules, and they both have London dispersion forces only, but the bigger the molecule, the more electrons that they have, the more probability you'll have clumping, and that means the bigger the molecule, the stronger the London dispersion forces are. So our next one we're going to talk about is where we actually do have a dipole-dipole attraction, and here I have carbon and oxygen, and let's just make sure that you know that these are nonpolar. So I'm going to put an oxygen with another oxygen there. So these are nonpolar molecules. Now here are polar molecules. Now there is a probability they could clump up, so all polar molecules still do have these London dispersion forces, but polar molecules have what we call dipole-dipole intermolecular forces. And so remember, we're talking about between two molecules, and we're going to be talking about between the same two molecules. We're going to assume it's in a cup with all these molecules. And here is our polar molecule. Oxygen is more electronegative, so it pulls the electrons this way and we have a permanent dipole. We have a negative side by our oxygen and a positive partial charge by our carbon. And again, these are attracted because we have positives and negatives and they attract like magnets. So let's just review. London dispersion, these are in polar molecules. And what I mean by that is polar molecules, the only forces of attraction between them is London dispersion, but London dispersion is in every molecule. And then we have where we have polar molecules and they have a dipole-dipole attraction, okay? So our last one on covalent, and technically the strongest for covalent, if we're talking about the same molecules, is hydrogen bonding. And this is just a super strong dipole-dipole interaction. It's so strong that we gave a special name to it, but it is two dipoles. And what it is a hydrogen has to be bonded to an oxygen, nitrogen, or fluorine within a molecule. And if it is bonded to that, then it's attracted to an oxygen, nitrogen, or fluorine on another molecule. So let's look at water. Water has a dipole, right? Oxygen pulls it this way, but this oxygen is bonded to a hydrogen. Since hydrogen is so tiny and oxygen, nitrogen, or fluorine is so electronegative, it makes this dipole-dipole attraction incredibly strong. So here we have oxygen bonded to a hydrogen, and then it's attracted to the hydrogen and the oxygen on another molecule, and this is a hydrogen bonding. If I also had hydrogen fluoride in the cup, because hydrogen's bonded to a fluorine here and it's attracted to the oxygen, that is considered hydrogen bonding. Remember, hydrogen must be bonded to an oxygen, nitrogen, or fluorine to have hydrogen bonding. So here's an example where it's not hydrogen bonding. Okay, so here we have hydrogen fluoride, which could potentially have hydrogen bonding. We see it does here, and it's attracted to a hydrogen, but this hydrogen is bonded to a carbon. It's not bonded to an oxygen, nitrogen, or fluorine. Even though there's an oxygen in there, the hydrogen must be bonded to an oxygen, nitrogen, or fluorine. So this is not considered hydrogen bonding, but it is considered a dipole-dipole attraction. So again, if it's to be hydrogen bonding, that hydrogen has to be bonded directly to a fluorine, nitrogen, or oxygen, and then it's attracted to another fluorine, nitrogen, or oxygen on a molecule. This hydrogen is bonded to a carbon, so it cannot make hydrogen bonds. Okay, but these guys are all, and it's this attraction between molecules that are intermolecular forces, not inside. Okay, so let's look at what type of intermolecular forces we find. Well, you have to draw a Lewis dot diagram to decide, is it going to be polar or nonpolar? Okay, so here I have two of the same molecule, hydrogen, hydrogen, that's nonpolar. This carbon's bonded to 4 hydrogens, so I have an even pull, they're nonpolar. If they're nonpolar, the only intermolecular forces they could have covalently is London dispersion. Here I have a polar molecule, so it would be attracted to another polar molecule that would be in the same cup, right? And I have dipole-dipole attraction because this is partial positive and that is partially negative. Okay, and then here I have a polar molecule, and I don't have an example there, so I will make that hydrogen bonded to a nitrogen, okay? And we have London dispersion, but since hydrogen is bonded to an oxygen, nitrogen, or fluorine, I have London dispersion always and hydrogen bonds. So look, every single one has London dispersion forces. There's a possibility my electrons could clump up. This guy does not have any dipoles, so that's it. This guy has dipoles, and it's not special, so it's a dipole-dipole attraction, and this is a dipole, but it's that hydrogen bonded to a nitrogen, oxygen, or fluorine, so we have London dispersion always, and it's also considered hydrogen bonding or hydrogen bonds. And I just drew the molecule here. Here are my poles lining up, my dipoles, And here we have hydrogen bonded to fluorine, so you can see another type of hydrogen bonding. Okay, now, if it's not covalent, there is one other one we like to talk about, and that's an ion dipole attraction. That's just an ion in solution bonded to a polar molecule. So if I dissolve salt in water, my chlorine becomes a negative ion, and my sodium becomes a positive ion, and it's attracted to these poles on water. So positive is attracted to the negative. Okay, and this is actually the strongest interaction because it's a fully charged particle. However, most people say hydrogen bonding is the strongest intermolecular force. That's because they're talking about only covalent molecules. But when we throw in an ionic compound, this will beat out hydrogen bonding for some things, okay? So now we are going to talk about the properties of intermolecular forces, more particularly how they affect certain properties. So intermolecular forces can affect properties like boiling point. So let's talk about the simple definition of a boiling point. That's just going from a liquid to a gas. So here I have all these liquid particles, and then they can escape and become a gas if I have enough energy. There's a very technical definition to boiling point that we'll get into. So right now I'm more or less showing you evaporation, but we're going to use this right now for boiling, okay? So right now this is staying a liquid because the attraction between the molecules are holding it tight and it's not letting it escape. But if I add a little bit of heat and I get some energy, they will start flying off into gas because that energy makes them vibrate and it gives them enough energy to break those attractions between molecules and turn into a gas. So the stronger these attractions are, the more energy I need to add to make things evaporate or boil. So weaker intermolecular forces have a lower boiling point and they need less energy, and that's why they have a lower boiling point, okay? And the last property we want to talk about is our surface tension. So surface tension is the attraction between molecules to minimize the surface area. And if you take a glass of water right now and a paper clip, and you very, very carefully place that paper clip on top of the water, okay, it's gonna float. There's my paper clip, here's my water. It'll float right on top of the water because these molecules are attracted so tightly, it's hard for the paper clip to push through because it's light enough. Okay, so again, these attractions between molecules minimize the surface area. That's why water forms a drop. They come together, minimize that surface area instead of spreading out. So water has very strong intermolecular forces, and that's the reason that bugs can walk on water and we can put that paper clip on top of the water. Okay, so there are our notes. We are going to do a small worksheet on intermolecular forces today. Tomorrow we're going to do a lab, and that is going to go over the properties and how intermolecular forces affect those properties.